All right, so now let's go over some of the basic tools for analyzing infinite series and determining whether they converge. Of course, not determining their values, but mainly just answering the question of whether they converge. So the first one we're going to look at is called the comparison test, and this is probably the most straightforward, but also, I mean, the most intuitively straightforward, but also the most general test and possibly the hardest one to use. So like conceptually, it makes a lot of sense, but it's difficult. It can be sort of difficult to apply it because basically the comparison test is all about very rough heuristics and estimation, and basically trying to manipulate some complicated expression in a way that simplifies it and always either moves the value up or down, so that you can make these like upper or lower bounds depending on whether you're trying to show a series converges or not. So let me just state the comparison test. You've probably, if you've taken Math 1B, you've definitely seen the comparison test. I'm guessing a lot of you have seen it someplace or another. But in this class, we'll sort of prove it formally. So here's the comparison test. So let series of AN be a series of non-negative terms. This is for all n. Then there are sort of two situations. So let me just write it out and then I'll kind of explain it. So BN, BN is a second series that we are interested in analyzing, and AN is sort of a series that we understand. So here, if AN, sum of AN is infinity, and BN is greater than or equal to AN for all n, then the sum of BN is also infinity. So hopefully this kind of makes sense that, if AN is a convergent series and then BN is kind of like, trapped, like the absolute values of BN are sort of trapped under the terms AN, then there's no way that the sum of BN could end up being like having like a bigger magnitude than the sum of AN. So that pretty much means that the sum of BN has to be finite. And if the sum of AN is infinity and BN is greater than or equal to AN, then you'd expect the series here to be at least as big as this one, right? So, but here's like the important thing to remember when you're using the comparison test is that, or at least when you look at the statement of the comparison test, is that these two sums of AN and BN kind of play different roles, okay? So the sum of AN plays the role of a simple series. So AN is a series we understand, and BN is the series we want to understand. So AN is kind of our like point of reference, right? AN is something we understand. We already know whether it converges or not, and we're using it, but we're comparing it to another series that's currently mysterious to us. And by using this comparison the right way, we can gain information about the other series BN, right? We can figure out whether it converges or diverges in certain situations. So let me just kind of go through the proof of this. I'm going to make a bit of an edit here. Okay, so for part one of the comparison test, we're trying to use the convergence of AN to prove the convergence of BN. And we know that the absolute value of Bn is less than or equal to An for each n. So the key here is to use the Cauchy criterion. So basically, and the triangle inequality. Okay, so what they say, sort of the key insight is for n greater than or equal to m, we have the sum the sum from k equals m to n of bk is less than or equal to, using the triangle inequality, this is less than or equal to the sum k equals m to n of the absolute value of bk. And in turn, because we know that each of these is less than or equal to the corresponding ak, this is less than or equal to the sum from k equals m to n of ak. Okay, and so basically, because ak converges, okay, well, let's use a different color here. So because this ak converges means that we can make this be less than epsilon. Oops. Right. But then by picking an n such that this is less than epsilon, because of these bounds, that forces this to be less than epsilon too. So right, for arbitrary pairs of n and m, where n is bigger than m and m is bigger than capital N, right? So so that shows that oops. So the series of bk is also Cauchy, hence converges. Note that this argument also actually shows that bk converges absolutely, because if you just if you go back to the conditions we were looking at here, right? The condition that the absolute value of Bn be less than or equal to An, if you just replace the series Bn with the series of absolute value of Bn, then the absolute value of Bn will still be less than or equal to An, because it's just equal to the absolute value of Bn. So this condition will still be satisfied for the series of the absolute value of Bn, which means that the series of the absolute value of Bn will have to converge as well. So in this situation, Bn not only converges, it converges absolutely, but we'll talk more about that in a sec. So for the second part here, let me just make a new page. So so for the second part, we're assuming that the series of An is infinity. Then since, let's see, right. So say Sn is the partial sums of the series of An, right? And say Tn is the partial sums, oops, not sums of the series of Bn, right? Then since Bn is greater than or equal to An for all n, we have Tn is greater than or equal to Sn for all n, right? Because Tn is just the sum of the first however many terms of the series Bn, and Sn is the sum of the first same number of terms of the series An, right? So term by term, Tn is less than or is greater than or equal to Sn, because each Bn is greater than or equal to each An, right? Or each Bn is greater than or equal to the corresponding An. So term by term, each of these Tn is bigger than the corresponding Sn, and then we know that since Sn approaches infinity, diverges to infinity, right? Tn also diverges to infinity. This is by a previous theorem or a previous fact that we've established. So that shows that So the fact that Tn approaches infinity is by definition the same as saying that the series Bn diverges to infinity. So, right, these are all positive infinity. So, okay, great. So that's the comparison test. One thing I want to sort of explain, maybe in case it was a little bit confusing, is like, why were there absolute values in part 1 and not in part 2, right? Oops. So why were there absolute values in part 1 but not 2? That's because actually, well, if you imagine putting absolute values here, then basically what could happen is that Bn could be, getting the absolute value of Bn could be getting very large, but the terms Bn themselves could be like alternating or just randomly being positive or negative, which means that instead of the series diverging to positive infinity, it would just like diverge completely, not even to plus or minus infinity. It could be something like, say An is like 1, and then like Bn is like -1 to the n times n, right? So then clearly the series of Bn just has no, defined value because the terms just keep getting bigger and bigger, but they're also alternating. So it doesn't diverge to plus infinity, but An does diverge to plus infinity. So basically the moral here is, I'll just write it over here. Saying something like x is less than or equal to y is more restrictive, more restrictive than x less than or equal to y, but x absolute value greater than or equal to y is less restrictive than x greater than or equal to y itself, okay? So sorry, I got a little bit cramped there, but basically, yeah, it's exactly what it sounds like. So if you require absolute value of x to be less than or equal to y, that's a stronger condition than just requiring x itself to be less than or equal to y. But if you require absolute value of x to be greater than or equal to y, that's actually less restrictive than just saying x itself is greater than or equal to y. Just think about it a little bit. Okay, so that's why there's sort of a weird asymmetry here. So let's just look at a couple examples of using the comparison test. So here's an example. All right, sorry, I had to make a little edit to refer to some notes. So here's an example of using the comparison test to show that a series diverges, okay? So consider the series n over n squared plus 3. This is one of the examples in the book. So when we look at this, so here, I want to kind of describe the process here, the sort of problem-solving process or something, the strategy here for generally analyzing series and determining whether they converge and then proving whether they converge, okay? So with pretty much any series, there's first of all a component of analyzing it, which is sort of figuring out whether you believe the series converges or diverges, okay? So you have to figure out what your own like guess is, right? What your own intuition is or whatever about whether you think it probably does converge or does diverge, because one of those two things is true, right? So you have to figure out which one, but then there's like a separate process of actually developing a rigorous argument that proves that your belief is correct, right? And so those two processes involve different tools and different strategies, and I'll kind of talk about that more later. But when I look at a series like this, right, like just in my own head, what's happening is that I see on the top, I see an expression which is basically, I mean, well, it's literally just n, right? But in sort of slightly more general language, the top is an expression whose sort of dominant behavior is, in proportion to n itself, right? Whereas on the bottom, we have an expression whose dominant behavior is governed by n squared, right? So this is a quadratic expression in n. This is a linear expression in n. So overall, okay, so basically intuitively, the terms, and I'm going to use this symbol here, they're similar, or proportional to, or approximately, whatever you want to call it. The terms are asymptotically similar to 1 over n. Okay, so we expect it to diverge. Right, because the series of 1 over n diverges. So these little extra complications, we don't expect them to actually make a difference. Okay, so now that we know what we believe, right, this is not an argument, right? This is not a proof whatsoever that this diverges, right? So now we actually need to use now we need to prove it. So we can use the comparison test for this. In general, when you make this kind of analysis, like if you come up with sort of like this simple expression, right, which helps you analyze whether it's converging or diverging, you'll be able to use the comparison test to compare this series to something related to this, although not exactly this expression, right? Because what we want basically is, so if we expect divergence, right, let's go back to the statement of the comparison test. We want to be using part 2 here, okay? Now look at what part 2 is saying. Remember, AN is the series we understand. BN is the series we're trying to understand. So BN is basically like n over n squared plus 3 in this case. AN is up to us to figure out, right? But we want to make it so that AN is something that's smaller than BN, okay? And that's a little bit tricky because 1 over n itself, okay, might be like our first guess as to what AN could be, right? But the problem is 1 over n itself is not actually smaller than n over n squared plus 3. It's actually bigger, okay? So what we want is AN less than or equal to n over n squared plus 3 with, and I guess, they should be non-negative too. And then the series of AN should be infinity, right? So unfortunately, 1 over n doesn't work. This is where we take the expression here to do this. A common strategy is to sort of take the expression here and then like modify it in ways that decrease the value, right? So, and still, preserve the divergence property of the series, right? So we can say that n over n squared plus 3, right, is greater than or equal to, remember, we're trying to reduce the value. We're trying to make an expression that's smaller, but still diverges when you take the series. So this is greater than or equal to n over n squared plus 3n squared, right? So I just put in an n squared here because, if n is greater than or equal to 1, oh, this should be like from n equals 1 to infinity. If n is greater than or equal to 1, then n, 3n squared is bigger than 3. So this is smaller than 3 because we made the denominator bigger here, right? Okay, so we made the denominator bigger. So the overall value goes down, but then this just equals n over 4n squared, which is 1 over 4n. So we didn't find that this is bigger than 1 over n because that's not true, but we found that it's bigger than a different constant multiple of 1 over n, that's good enough, right? Clearly the series of 1 over 4n diverges because the series of 1 over n also diverges, right? So AN equals 1 over 4 over n, or 1 over 4n. Then, so we're taking AN equals 1 over 4n. Obviously, that's not the only choice. There are like infinitely many good choices you could make for AN. This is just the one we arrived at with this method, right? So then the series of AN is plus infinity, and by, this sort of logic here, we know that AN is less than or equal to BN for all n. So by the comparison test, we see that the sum of Bn is infinity, okay? So that was using the comparison test to show divergence. Let's just look at an example where we show convergence instead. So let's look at the series 1 over n squared plus 1, okay? Here the terms are, similar to 1 over n squared. So we expect convergence, right? So now what we want is actually, we want another series whose terms are bigger than these, bigger than the absolute value of these, right? So we want an greater than or equal to the absolute value of 1 over n squared plus 1, which of course is just equal to 1 over n squared plus 1. So as long as an is bigger than 1 over n squared plus 1, we're good. In this case, it's very easy. What we can do is just like delete the 1 in the denominator. So we can take an equals 1 over n squared. That's bigger because the denominator is smaller, right? So so then series of an converges, and if this is the series of Bn, we have absolute value of Bn is less than or equal to an. So this is for all n. So the series of Bn also converges by the comparison test, right? So just remember that if you're trying to show divergence, you want to choose a series, another series, a comparison series whose terms are smaller. If you're trying to show convergence, you want to choose a comparing series whose terms are bigger, okay? Try not to get that flipped around, because that's a really common thing that people do. Flip the direction they're trying to go, and yeah. If you find, if you take this series and then find another series whose terms are larger and which also diverges, you've said nothing about what this series does. It could converge, it could diverge. Both of those things are compatible with a larger series whose partial sums diverge, right? That's just says nothing. So yeah, anyway, that's the comparison test, and I will talk about the root test in the next video.